Okay, welcome back to Module 4, their second video. This part I'm going to get into hyperspectral remote sensing systems. This has been an ongoing and improving technology that we've been seeing in industry. So for a long time it was just used for research because it was very costly, it required a lot of computing power, and it was very hard to handle. So now with computers being the way that they are, does a much better job of being able to handle the data. So now we can use hyperspectral remote sensing systems in many different applications. So what hyperspectral means is a lot of numbers of bands. That's what it all comes down to along the electromagnetic spectrum. So multispectral means many, hyperspectral means lots and lots and lots and lots. So we use the definition that hyperspectral remote sensing acquires images in many very narrow contiguous spectral bands throughout visible, near-infrared, mid-infrared, and thermal infrared portions of the electromagnetic spectrum. I gotta sneeze. Excuse me. So we can see hyperspectral, and you can see that they're connected. There's no gaps in between them. So and it's really narrow. So we can see that the blue spectrum, for example, has 1, 2, 3, 4, 5 different bands. Where in, for example, Landsat, which is a multispectral, there's only one band. So this gives us a lot more information because we get like 5 different pieces of information, and there's no gaps in between any of them. So we get even more information because they're not leaving information out. So this provides us some really good insight into what is happening on the ground. So that moves us into objective 4.6, which is identifying some properties of hyperspectral remote sensing systems. So some of the hyperspectral properties that we have, it allows us to discriminate features that have absorption and reflection characteristics and where that happens on the electromagnetic spectrum. So this is for those of you, you guys in environmental technologies, you would use spectrometry, and this is the remote sensing version of it, creating images using spectrometry. So now we can really look at the entire electromagnetic spectrum and figure out what gets absorbed, what energy gets absorbed, and what energy gets reflected. So with really big bandwidths, which is in the multispectral images, what this third topic or third bullet point means, is that there might be some hidden change, very minor, that we completely miss because it's just bulked in with a single band. And we only get one number out of a single band in the multispectral system, where if I can get 5 different numbers out of the hyperspectral, I might actually see something a little bit different. So this was originally limited to laboratory tests or ground surveys, but now they've moved up into, like, there's a couple space-based ones, and there's quite a few ground-based ones as well, and airborne as well. So we can now see features in a feature that we couldn't before. So here's an example. So if we went out and did used a spectrometer and tried to identify these different types of minerals, then we would be able to see all this information. Hyperspectral, we can look at every segment, for example, all the way along, but you can see how much information, like Landsat 7, for example, would be missing. So all we could see what's different between these is perhaps one value that it's like, oh, this one's higher than this one, and this one is maybe higher than this one, because these dips might make it really confusing. And then this one and this one might end up being looking the same. You can see another example here with calcite and dolomite, and the difference is going to be so minor that it's going to be really hard to try to identify between the two of them with a Landsat band. But if we can get all of these, every single band, making a much narrower and identifying the data in a much narrower bandwidth, then we can actually start drawing these graphs, and then we can start identifying which is which. And here, like for example, calcite and dolomite, they have generally the same curve, but there's this one little tiny difference. And that little tiny difference might be the most important one and show us what we need. So here's an example with hyperspectral images. So alunite is showing up here in A, but let's go up here. Do we see anything in that region? No, not really, not really, not really. We can keep going along. And then we start seeing something showing up right here. And then it's darker and darker and darker and darker, and then all of a sudden it's gone again. So if we didn't have these individual bands from 12 or 2.12 to 2.18 and show those individual bands, we wouldn't see these three spots here, because the rest of them are gone. So that's why we like hyperspectral, because it identifies just that little bit of difference in between what we had before and what we have now. Like with my multispectral, when I say before is multispectral, and then now we have hyperspectral. So now we can really see those differences. But you really have to go through a lot of bands to be able to see something like that. So I didn't do this slide very well. But the problem is that our computer's display is only limited to 3 bands. So that should say 3. So you can only see red, green, and blue. And we can take any band, like so even if I take 5 blue bands and I put 3 of those into red, green, and blue, I'm going to be able to see the difference between all of those bands, and I'm going to have that visualization. So because of that, we need to come up with another way to show the data. And so we use a pixel-based analysis, and we use something called a spectral library. So those of you who've used a spectrometer, we're creating spectral signatures using the data that we get for every single pixel. So we get one of these nice graphs showing us the reflectance and the wavelength. Then we can take, for example, we take this data here and we can compare it to a library that has been set by other scientists that have done this over and over and over again and said this is the shape that this particular mineral or organic material is going to have. So then we can compare it and say, oh, okay, this one matches this in the library, so I now know what that material is. So this is a way that you just can't do interpretation with multispectral. You just can't do it at all because we just don't have enough data to do it. So that we call this, oh, by the way, I can go back here. This is called an image cube. You probably need to know that at some point. This is an image cube, and we use an image cube analysis is what is the name of this. Spectral signatures and spectral library come from image cubes. So that's where that comes in. Okay, some really quick hyperspectral scanners that we have in space. We have quite a few of them. Hyperion, which is the old version. Then we have the HYS SWIR, HYS VNIR, and the HYS IS. So the Hyperion was 220 bands and covered the spectrum. Now the SWIR one has 150, VNIR is 60, and the IS is 316 bands. So that's how many layers that you have to look through in your databases. The HSI, which is a different system, has 232 bands. So lots and lots of data, and they're coming from space. The reason there's not many hyperspectral scanners in space is because there's a trade-off between spectral resolution and spatial resolution. So this has really high spectral resolution, which means that my spatial resolution is very poor. So in saying that, then we can move it down into the atmosphere, and there's lots and lots of different airborne scanners. So there's SnapScan, which was just one that I Googled. It's got more than 100 bands. You can actually get them customized to what you want. They work with that. Avirus is 224 bands. Cassie is 288. You can see the different ranges that they work in the spectral region. But there's just like there's many more. Like anything to do with like on the Earth, anybody can go out and design one of these scanners. So there's lots of different kinds. So objective 4.8, which is our last one, is identify applications with hyperspectral. So I just put together like a little summary of the different kinds of applications, just because you can go on and on and on. There's so much you can do with this as well, because if you're trying to identify materials, then you use hyperspectral remote sensing. So we can look at the atmosphere, so we look at water vapors, we can look at cloud properties and aerosols, and then ecology should be its own thing, so I'm going to make sure I fix that before I put this up onto the webpage. Ecology, so we can look at chlorophyll count, leaf water, cellulose, pigments, lignin. You do measurements with that, like from a distance. Then we can get in geology, which like looking at mineral and soil types. Coastal waters, we can look at chlorophyll as well because of the algae, phytoplankton, different organic materials, suspended sediments, so lots of stuff we can do with water. Snow and ice, so we got snow cover, grain size of snow, melting rates of snow. So there's two different stages that snow goes through before it starts to melt, and you can actually identify that with hyperspectral. And last but not least, you have all kinds of other commercial stuff, so mineral exploration, agriculture, and forest production. So again, open your mind and think, what could I use this for an application? And then you've got it there. So here's the references. The references also attached to the previous one, but that is everything for hyperspectral. So it's not a big topic in this class, but it is something that's really becoming more and more popular. More and more companies are looking for people who can process hyperspectral. So it will eventually become a very important part of remote sensing and possibly take over multispectral stuff. So multispectral will be considered low end and hyperspectral will be considered the high end. So that's everything, and I look forward to seeing you guys in class in Module 5.